Hi there. Today we're talking about Le Chatelier's principle. He's a classy looking guy, as you can see, so let's get started. Now Le Chatelier's principle has to do with equations and what they do with stress, but let's think of it from your perspective first of all. You're an average student in a high school and everything's going fine. You've got a beautiful week, everything's planned, and then suddenly a stress is added. Your stress would be suddenly you have a test on Friday. You didn't see that coming, they didn't tell you it was like a pop quiz kind of test. So now you have a test on Friday and you've got to study because you haven't been doing much. That just creates a really imbalance in your system and your world. So what are you going to do? You're going to sleep more, you're going to eat breakfast that day, you're going to study, and it might mean that you can't quite do this assignment yet, so you're going to turn it in late. See, the thing is, you have your equilibrium, you're happy, life's going fine. You add a stress, you got a test, and so you have to do something about that. You have to shift your world. You're going to eat better food, you're going to sleep more, and then maybe you're not going to get that one paper done. Well, equations have that same deal. You can see this equation here. It's perfectly happy. It's in equilibrium. Everything's great until we add a stress. And it has to do something to relieve that stress, just like you and me. That's what Le Chatelier's principle says, just in fancier words. If a stress is applied to a system in dynamic equilibrium, the system has to shift or do something to relieve the stress. There are three types of stresses that equations can have: concentration, temperature, and pressure. And we'll take them in these orders. So here we go. Concentration is going to be our first one. So everything is in equilibrium and everything feels pretty happy. I can see I've got my equation here. I'm going to write the KEQ for it. Products over reactants. I'll put my H2O, which is a product, and my CO2, which is a product, over my reactant, H2CO3. I notice that they're all aqueous or gases, so I have them all in my KEQ. Sorry about the writing's not great. So everything's in equilibrium, and my KEQ is a set number. What I'm going to do now is stress out the system. And the way we're going to do it is by using concentration. That's one type of stress. So one way to do that is let's add more of this. Oh, that's a big fat pen. We're going to add more water. Now suddenly this number on top is really big, too big. You can see the KEQ isn't the same because now we have too much water, and the number that we get up here is going to be greater with more water. So the system is stressed out. It has to remake equilibrium. To do that, it's going to shift the equation this way for a little bit of time, so my arrow for a moment will be a little bit going that way, but extremely going to the left, until the reaction can remake equilibrium, and when it does, it'll be back at that number, the same number it was before. Now we might have different amounts of water and CO2 and carbonic acid, but the number, the ratio, will still be the same. Let me show you what I mean with a different screen. Okay, you can see we've got this equation. Everything looks lovely. You can see the macroscopic view. So taking a look here, if you took all of these three colors and kind of like three Kool-Aids and added them together, can you imagine you would get this colored beaker, this orangish color? It's in equilibrium, everything's pretty happy and things are great. And what we're going to do is stress it out. I'm going to click on the add NaSCN. Now when NaSCN goes in the bucket, it's an ionic compound, so what you're really adding is Na and SCN1 minus. Well, in the equation, SCN is right there. So what I'm going to do is add to this side of the equation. It's like a teeter-totter. This side of the teeter-totter is too heavy. We've got to shift the reaction to make it level out. If you add an SCN, the reaction will shift left. In other words, it will make the reactants faster than you are making the products until we can remake equilibrium. Let me show that by actually doing the button. Here we go. We're going to add NaSCN. Look at, they added a huge amount. It's not in equilibrium, but it's shifting. And now we get less of the SCN, and we've got a lot of FeSCN. So we can see we now have different amounts of the red, yellow, and gray. But if I wrote the KEQ for this, the KEQ number would be the same. The amounts of each reactant and product are different, but you can think you can get a fraction like 6/10 is the same thing as 3/5. They're different numbers, but we still get the same fraction. Same thing here. We have different numbers or different colors, amounts of these bars, but the same fraction every time. Take a look at what my beaker looks like. It's a bright red, and if you put in your mind these three colors together, it would make sense that you would get a bright red color, and that's what you'd see. It's still at equilibrium, but there's just a lot of FeSCN that's making it so red. Let's go back to normal and say we're going to remove the Fe. If we remove the Fe, it's as if we don't have any of this anymore. Well, that's not equilibrium. We have to have some of it. So in order to remake it, the reaction would have to shift to the right. It will make more of the Fe until we can remake equilibrium and get the same KEQ value. So let's give it a shot. All the Fe3 plus is going to go away. There it goes. We've got to remake it so some of the red stuff starts to make some of the yellow parts. And we can see in the end, if you take these three colors, it would be a more yellow color. It's a bit drastic yellow, but it would be more yellow as we lost so much of the red. It's remaking equilibrium, just at different amounts. Okay, so that's stress number one. Let's go on to a different stress. We're going to look at temperature. In order to do temperature, you have to know if it's endo or exo. So in this case, I'm looking at an exothermic reaction. Exothermic means producing heat. Producing heat makes heat as a product. That's why I put heat in my reaction, to show that it's a product. So when you think about exothermic, think of it as heat as a product. When you think endothermic, think heat as a reactant. And actually write it in the equation. That'll help you out. Because now that we have that, it's really no different than the concentration thing. So I've got my equation, and let's say we're going to heat it up. We're going to make this reaction hot. If you make it hot, aren't you adding a lot of this? Suddenly this side is too heavy. If it's too heavy, it's too stressed out, we have to have the reaction shift to the left. It'll move left. In other words, it will make more of these reactants by using up these products in order to remake equilibrium. Once it shifts enough, then it'll stop shifting and we'll have an equilibrium set again until you do something else to it and stress it out some more. A different way we could stress it out is if let's say we make it colder. If we make it colder, it's as if it doesn't have any heat anymore. And if it doesn't have any heat, it's as if it doesn't have one of its products. And so we have to remake that. The reaction will shift to the right, in this case when you make it colder, because we need to make more of the products. We need to remake the heat that we stole and took away. For Le Chatelier's principle, you want to focus on which way it shifts. Shifting left, shifting right. So I'm going to give you an example like, I'm going to do this to the reaction. Will it go left or will it go right? That's what you want to focus on. Let's go to our third one. Pressure is the third one. Now pressure is very specific. Pressure only affects equilibrium with an unequal moles of gaseous reactants and products. Now we can only look at gases because gases are the only thing we can pressurize. Like if you think about it, the only way we can change pressure is if you change the volume of the container. If you had a solid, could you fit it in a smaller container? No, it is what it is. Or if you had a liquid, a bottle of water, you can't fit the liquid in a smaller bottle of water. So the only thing we can affect with pressure are gases. In this equation, I happen to have all gases, so that makes it nice. And what I need to do is look at the total number of gases. On the left side, I have 4 moles of gas, 1 N2 and 3 H2s. On the right side, I happen to have 2 moles of gas. Okay, so step 1 for pressure, look at how many gases you have on each side. If one of these happened to be a solid, then I wouldn't have these numbers, but I have 4 moles on the left and 2 moles on the right. So now what I'm going to do is add a stress to it. The stress that we're adding here is pressure. The way that you can change the pressure is change the size of the container. Like let's say I've got a container, and it's this size, it's capped off right here. And all of these gases are inside there. They're at equilibrium and everything's great. I'm going to take the volume and make it smaller. Now I'm going to make all those gases live inside this hole, this space. Well, if they have a smaller volume, decrease in volume, it's an indirect proportion. So we have to increase the pressure. This increase in pressure creates a stress on the system, and we have to alleviate that stress. So here's what we're going to do. If we create a smaller volume, I've got two options. I've got 4 moles or I got 2 moles. The problem is that you have to think about gases as a form of like people. If you had a big room, you would be fine with lots of people in there. You could stretch and everything would be fine. But if suddenly all these people are living in a smaller space, in a smaller volume, you don't want as many people in there. It's too crowded. Same thing with gases. I've created a smaller volume, so I've got to relieve that stress. Which way would I go? Well, to the side where there's fewer people. In this case, we're looking at moles of gases. So I'm going to shift the reaction to the smaller moles of gases, in this case to the product side. Alright, now it's your turn to see how you can do. I want you to go to that demo website that I was just on and click on the temperature button. Investigate by clicking on the different buttons and seeing what happens. Pay particular attention to the color of the big beaker that you see. Then go to the Google form and answer the questions. We're going to do practice tomorrow, so I'll see you then.